In this video, we begin talking about Chapter 3. In particular, we're going to focus on sections 3.1 and 3.2, which I'm deciding to mix together because the concepts are very similar. Here, we'll be discussing predicates and quantified statements. Here's a quick outline of what we will be seeing in the next few videos. And we begin with the reason why we need quantified statements. The reason why we need quantified statements is because of arguments such as this one over here. It says all men are mortal, Socrates is a man, Socrates is immortal. There's a special statement or a special word showing up in the first sentence. It says all men are mortal. So we want a way to be able to refer to statements like that. This is the reason why we have something called predicate calculus. In normal English, the word predicate usually refers to the part of the sentence that gives information about the subject. So for instance, saying James is a student at Southwestern would imply that James is the subject and is a student at Southwestern College is the predicate. So the predicate itself, think of it as like a function. It contains a certain amount of variables, and it becomes a statement when numbers or values are substituted in place of those variables. The domain of a predicate is the set of values that can be substituted into the variable. For instance, the predicate p of x in this example is x squared greater than or equal to x. So obviously, that could be true and it could be false depending on the value of x. In this particular problem, I want the domain to be the set of all real numbers. So the first part of the question is, what is p of 2? And what is p of 1/2? And the second part of the question is we're going to try to figure out which one of those two is going to be a true statement and which one of them is going to be a false statement. So to figure out what p of 2 is, all I have to do is replace the x in my predicate with the number 2. And so I get 2 squared is greater than or equal to 2. For 1/2, I do something similar. I replace the x with 1/2 to get 1/2 squared greater than or equal to 1/2. So these are the solutions. Now, some of these can be simplified even further. And once I simplify them, I can now talk about which one of them is true and which one of them is false. For instance, the first predicate gives me that 2 squared is greater than or equal to 2 when 2 is replaced, which is equivalent to saying 4 is greater than or equal to 2, which is a true statement. Similarly, when I put 1/2 into the predicate, I get 1/2 squared is greater than or equal to 1/2, which can be simplified to 1/4 greater than or equal to 1/2, which is a false statement. Let's talk about universal quantifiers and universal statements. You're seeing a brand new symbol on this slide, which is the upside down capital A. This is the symbol that we're going to be using to denote the words for all or for any. So when you want to talk about everything or anything, you use that symbol. We call this a universal quantifier. The statement for all x in the domain, comma p of x, is known as a universal statement. For a universal statement to be true, you have to be true for every possible x variable that can be substituted. If one x makes the predicate false, then we call that x a counterexample, and the universal statement becomes false. There's a second symbol that we are going to see in this section, and it's basically the capital letter E written backwards. This is the symbol for an existential statement. So the symbol replaces the words there exists, there is, or at least one, or some, and so on and so forth. It is known as the existential quantifier. An existential statement has the following form to it. There exists an x in the domain, comma, p of x. Sometimes it is pronounced there exists an x in the domain such that p of x. An existential statement is true when at least one x in the domain makes it true. And it's false when every x in the domain makes the predicate false. In combination with the existential statement, you're going to see me using oftentimes this symbol. It's the backwards belongs to symbol. That symbol is going to represent the words such that. Sometimes I'll also write st for such that, or when it's not confusing, we will use comma, just like they did in the statement in the definition. Let's think about how we can possibly rewrite something like this. There exists at least one real number x such that x squared is less than or equal to 0. So first of all, what I'm hearing when I start reading the sentence are the words there exists. These two words remind me that there's an existential, so there's going to be a backwards looking e to represent that. Next, I'm hearing the words one real number. So my domain in this problem is going to be the real numbers. I'm hearing the words such that, so that will be a comma or backwards belongs to. And finally, the predicate itself, x squared less than or equal to 0. So using this knowledge, I can rewrite my expression as there exists an x in R such that x squared is less than or equal to 0. Again, we're not discussing whether this is true or false yet. We're just trying to translate from words to symbols the statement that's written in the example. Let's try it again one more time. In this case, though, we're going in the opposite direction. We have symbols, and we would like to rewrite it without symbols, without these quantifier symbols, basically in words. So it's saying for all x belongs to R, this is the symbol for all real numbers, this is the symbol for belongs to. So for every R in the real numbers, x squared is greater than or equal to 0. That is the predicate. So because I'm seeing the for all symbol, I know that this is going to be an example of a universal statement. The words for all are going to be written first, then x belongs to R means that I'm dealing with a real number. So for every real number x squared is greater than or equal to 0 can be translated in words to mean the square of x is greater than or equal to 0. So one possible answer is to say the square of any real number is non-negative. Or equivalently, I can say given any real number, and you can see the words for all implied in there. I'm not writing any words for all, but I'm saying for any real number, its square must be non-negative. So there's more than one way to translate from symbols to words. Finally, let's try one more time to rewrite there exists m in z plus such that m squared equal m in an informal way without using quantifiers. So again, this is an example of an existential because of the words there exists or that backwards looking e. M in z plus means that I'm dealing with a positive integer that we're calling m in this problem. M squared equals to m tells me that the square of the integer is equal to the integer itself. So one possible answer might be something like this. There is some positive integer that equals its own square. Or I can say there is a positive integer that equals itself when squared. Okay, some students in Math 365 will pass. Again, this is an example of an existential because I'm saying the words some student. The domain is a person in Math 265, and the predicate is that that person will pass. So one possible solution is to write there is S in Math 265 such that pass S. In this case, I'm using pass parentheses S, which is what we're calling, or we're treating it like a function basically. So the passing in this case is being treated like a function, and S is the variable that the function accepts, meaning it accepts the student name and it tells you whether the student will pass or not.